Alright, back again with some more Fourier. I'm going to make it a little bit more complicated. Last time we pointed out, we said that we can represent a periodic function with a whole bunch of scaled building block basis functions, where these building blocks were complex exponentials, which we showed were orthogonal, and we could calculate the appropriate scaling factor for each one of these exponential sinusoids. We're doing really well. I wanted to point out that the frequency of these exponential sinusoids is sort of embedded here, where we've got the fundamental frequency multiplied by some integer value. So we have a whole bunch of them. And that integer value, can go from negative infinity up to infinity. Note that in many cases, we don't actually use all infinite number of them. That might be impractical, but we've got a whole bunch of frequencies. We also have corresponding scale value for each one of these frequencies, or each one of these basis functions. I'm going to rewrite that out and note that this corresponds to some cosine function, which we're pretty familiar with, and we can get the coefficients here just by observation. So if we said we've got an x of t value that's a cosine, we can represent it more like a Fourier series, where our scalar coefficients for the complex exponentials are a over 2 in this particular case. And we can actually take that very basic example and start plotting it like we did in the last video, where that looks like a cosine, and it looks like we've got one period t naught, and that's related to our fundamental frequency. Makes sense. It's got an amplitude of a. We can write that out in the Fourier series representation, and it can be also represented in the frequency domain with the stem plot. In this case, the amplitude's a over 2. Because when we convert from cosine to complex exponential, we get the over 2 multipliers. So again, you should be able to go back and forth between these stem plots, where this pair represents a cosine, and this time-varying cosine that you're pretty familiar with. The frequency that we're plotting these stems at is just simply k times omega naught. So this was for a and some k times omega naught. Let's just ground it a bit with some real numbers. You might start to look at this and guess what a might be and guess what k might be. If we convert this to an exponential form, we've got 5 over 2. And we've got k times omega naught. What do you think k might be? Well, putting it into our stem plot, we then have the amplitudes of our scaling coefficients to be 5 over 2, and they appear at frequencies negative 4 omega naught and 4 omega naught, corresponding with the original frequency of the sinusoid. Again, you should be able to go back and forth these. I sort of skipped over the fact that one period of this sinusoid should be 2 pi over the frequency of it. In this case, it's 4 omega naught. Make sure that makes sense to you. Cosines can also have a phase shift. This is pretty important. In fact, there are 3 different things that actually characterize the cosine: the phase, the frequency, and the amplitude. We just talked about the amplitude and frequency, and we saw how those showed up in our frequency domain stem plots. Let's see how the phase comes into play. When we actually convert to the complex exponentials, we know that whatever is in the parentheses here of the cosine is going to be put up in the exponential and multiplied by j and negative j. That's how we convert back and forth between our cosine and our complex exponentials, as well as dividing by 2. If we multiply that out, we can actually get a couple terms here. We've got our time-varying complex exponential and our non-time-varying. For both of these terms, time-varying, non-time-varying. Now, we note that our scaling coefficient c of k actually will include this e to the j theta, where theta is what we call our phase shift. Similarly, the other scaling has an e to the negative j theta. So we can write out our scaling coefficients, which may actually be complex. Or in this way, we've actually generalized a representation to include complex scaling coefficient. So let's ground this with an example. In this case, we've got a cosine of amplitude 5, frequency 4 omega naught, and phase of pi over 4. You can see in our plot that we still have amplitude 5, but the whole curve has been shifted by pi over 4 radians. It still has the same period or same frequency of 2 pi over 4 omega naught. It still has the same period of 2 pi over 4 omega naught because of the frequency of 4 omega naught. And this might all look a little bit different in the frequency domain. So let's first break out into our complex exponential forms, which looks like our Fourier series. And you can see now we've got these j to the pi over 4s, or e to the negative j pi over 4. That wasn't there in the previous example. And we can actually plot this in a couple ways. In different texts and different online media, or different papers even, they're going to have a different way to represent the stem plots. Here's one way. So we've got 2 terms, each of amplitude 5 over 2. So you see the 5 over 2. And they're at the different frequencies of negative 4 omega naught and 4 omega naught, corresponding to the appropriate frequencies where k equals 4. But we've also added in an e to the negative j pi over 4 to complete this scaling coefficient, and an e to the j pi over 4 to complete this scaling coefficient. That's one way to sort of display the phase with your stem plot. Here's another way where we've got the amplitude of 5 over 2 displayed in one plot and the phase portion, the negative pi over 4 and pi over 4, displayed in a phase portion of the stem plot. So you're sort of using two different parts or two different plots. Different people are going to use different representations. You probably should be nimble and be able to sort of look at both and understand what's going on. So to make sure you're on top of all this, we're going to go through another activity. Get your pen and paper handy. In this case, we're given some function which looks to be sinusoidal. It's 5 plus 5 cos 4 pi t minus pi over 4. And we're given a fundamental frequency of 2 pi radians per second, if that matters. Draw the corresponding spectrum or stem plot. I would suggest you pause the video, but if you want one hit, make sure you realize which part is the amplitude, phase, and frequency of that sinusoid. Also, another hint, you can break it up into term by term. All right, here we go. Let's take that function, break it out like I just suggested, into 5e to the j 0 omega naught t, which maybe seem a little pedantic, but it actually is there to reinforce that each one of these terms can be broken out into a complex exponential. The corresponding stem plot is going to have one stem for each term here. And the first term has a magnitude of 5, and it's got a frequency of 0. There it is. The next two terms correspond to frequencies of 2 omega naught and negative 2 omega naught. So 2 omega naught and negative 2 omega naught. Each of them has an amplitude, and it looks like it's complex because there's that phase shift of negative pi over 4. So there's the amplitude corresponding to the 2 omega naught, this amplitude, and another amplitude, which is complex, corresponding to the frequency of negative 2 omega naught, right over here. There you go. To summarize, any sinusoid defined by an amplitude A, frequency k omega naught, and phase theta can be represented as a Fourier series with two scaled basis functions. So when we write them out as a complex exponentials, we get two terms for every cosine, each consisting of a possibly complex scaling coefficient. We can plot it out in continuous time domain, and we can plot it out in frequency domain as a stem plot, or sometimes we call this a spectrum.